We need to look at the terms we're going to use in this video. So let's start with this information here. Consider a positive and continuous function. Okay, the function is continuous and the function is above the t-axis, right? That's this horizontal axis. The function is above that, so on this vertical axis it's always positive. And the function is this function. Now that's that. That's what that purple line is representing. Over the interval t is greater than or equal to a and less than or equal to b. So t can take any value between a and b. The area enclosed between the graph of the function, so that's that line there, the purple line, the t-axis, which is the horizontal axis, and the vertical lines t equals a and t equals x. We've taken that point. We're not finding it all the way to here. We're just stopping here. So this is the area we're concerned with here, where x is greater than or equal to a and less than or equal to b. So x falls between a and b. It's defined by this definite integral here, where the area is the definite integral of that function between a and x, between a and x. So we've got our boundaries, we know our function, and we can write the definite integral with respect to t. It's not x anymore because this horizontal axis is t. Now let's have a look at this one here, this definition. Now all of this is repeated from here. Okay, we already know this, that the function's greater than or equal to 0, it's continuous. They told us that here, it's positive and it's continuous. The area enclosed between the graph of f and the x-axis over the interval is that, well actually the t-axis, right? The t-axis can be found with that definite integral. So that should be the t-axis. Basically it's the horizontal axis, right? So that is what that is. It's the definite integral. Okay, let's look at this diagram first. We know how to differentiate from a function. So let's consider this capital F as the function and this smaller f is the derivative of that function. Well, integration is often called anti-differentiation because we're undoing what we did when we got from there to there. We're now going back. Now let's have a look at this equation here. Basically, we're equating, that's the original function, right? The derivative is notated by f dash x. So that's the same as that. That's why they say it's the same. It's the same because the derivative of that is capital F dash x, which they're representing here now with a small f. And they're saying that this function here is the derivative of that function. That's what that means there. Now, what about this part? Now, we're just talking equivalency here. We're just saying that if you took the derivative of that function, you would get that function because we've differentiated the two. And anti-differentiation or integration is going the other way. That's all it's saying. So if you had a function and you did the opposite to differentiation, you would end up with that function. And if you had a function and you did differentiation, you would end up with that function. They are linked. And so when we have a look at this integral between a and x, between t equals a and t equals x, then we've just said that the integral of this function is going to be the anti-differentiation of that function, which we've already defined through here as what we had differentiated from. Then this notation here represents the value of that integral at x, and this one here represents the value of that integral at a, and we subtract them because we're only interested in the domain t equals a to t equals x. Let's look at this example. This function here, the capital Fx, that goes in that box there, so that'd be x squared plus 1. If you differentiate that, you're going to get 2x, okay? Because we differentiate that, we get 2x. So if this is x squared plus 1 and that is 2x, as represented here, we know that because we said this function is actually the derivative of this function. That's what that says. Because the derivative equals 2x. So if we put x squared plus 1 here, then we know that's going to be 2x. So we've established the relationship between these two now using this example. If this is x squared plus 1, the derivative of that is 2x, so we put a 2x in here. So we say that the derivative of this is that, and the antiderivative of this is that. So the derivative of x squared plus 1 is 2x, and the antiderivative of 2x is x squared plus 1. And just let me make one distinction here. I did say the antiderivative, but on purpose they've got an antiderivative, as you'll see later. Okay, it is just an antiderivative, it's not the antiderivative, because we really don't know what that constant is when we go back the other way. Can you think of an antiderivative for this function? Well, what we've got to do is, in our minds, we just say, okay, that's the derivative. Now, what was the function that would be a derivative for? How could we find that? Well, the answer actually is x cubed, okay? Because if you think about it, if you take the derivative of x cubed, and you know how to derive a function, if it's x cubed, the 3 comes down to the front and it becomes 3x, and then it's n minus 1. That's the indice, so that becomes 2. So the derivative of x cubed is 3x squared. So the antiderivative of 3x squared is actually x cubed. The good news is you don't always have to just do everything in your mind. Just like there was a formula to find the derivative of a function, there's a formula to find the antiderivative of a function. What I need to do is make a video of investigation 3 which precedes this, because it's very clear then the relationship between these two functions here. Example 11, find an antiderivative of y equals 4 plus 2x. When you see a question like this, you have to find out, in your mind, you think that's the derivative, so what function is that the derivative of will give you the antiderivative. So this, and we can go term by term. So to get a 4, the original one had to be a 4x. When I say original, a function that would give this derivative would have a 4x in it. And a function that would give that as a derivative would have an x squared in it, because we're reversing how we actually got to a derivative. And that's why the answer there is 4x plus x squared. They're using the capital F here. An antiderivative of y equals 4 plus 2x is a function f whose derivative is 4 plus 2x. Right? So when you find the antiderivative, you think of that as a derivative and you go back the other way. The derivative of 4x is 4. Okay, so if we go the other way, how did we get to 4? Well, 4x, the derivative of 4x would give us 4. The derivative of x squared would give us 2x. So we put those two terms together and we say the derivative of 4x plus x squared is 4 plus 2x. So the antiderivative of 4 plus 2x is 4x plus x squared. B. Find a function y equals gx when the gradient function is dy dx equals 3x. Well, that's the derivative. And if that's the derivative, we just got to go back the other way. How did we get to 3x? What would give us 3x? What function would we differentiate to get 3x? Well, if we go the other way, you could think of it as saying, well, maybe it's x cubed. But if it was x cubed, the derivative of x cubed would be 3x squared. Well, it's not 3x squared, it's 3x. What did we bring down from here? If this is x now, the actual function that we derive must be an x squared. So we must have brought down a 2. If we brought down a 2, there must already be a 1.5 here, because 2 times 1.5 would equal 3. So the function that we derived and we got 3x as the derivative must be 1.5x squared. And that's what we find here, 1.5x squared. If the gradient function is that, then the derivative is 3x, right? So that tells us that. We know that's the derivative. The function g is a function whose derivative is 3x. So what function did we derive to get 3x? Well, it had to be 1.5x squared, because when we bring the 2 down in front, we get 2 times 1.5 is 3, so the derivative of that is 3x. Example 12, consider the definite integral where x is greater than equal to 0 and less than equal to 1.5. A, draw on a diagram the function, that particular function, remember it's with respect to t, not x, and shade the area represented by that definite integral. And that matches our notation that we're used to. We've got the lower limit, the upper limit, we have the function, which is that function, and it's dt because the horizontal axis is t. The vertical axis, they've got y, which is the same as that, so they could just as well have put that notation at the top of that axis there, because that's the vertical axis. We know it's of the form y equals mx plus b, though it is actually written as b plus mx, or in this case mt, where m is minus 2. We've got that negative slope. It crosses at 3, so we know that point is 3. the reason they chose this domain, but x is greater than equal to 0 and less than equal to 1.5 is if you put 1.5 into the function value is 0. So that's that point there. And all these examples are based on continuous, which this is, and also positive functions. It's above the t-axis in this case, the horizontal axis. Okay, so that's our function. Now, it's between 0 and x, where x is less than 1.5 and more than 0. So somewhere between there and 1.5, they've drawn t equals x. Now it says you can use your GDC to draw the graph. Hopefully you don't. You can do it without the GDC, but it's always good to check, I guess. Shade the area under the graph of f between t equals 0 and t equals x, just like that. So you could have just put that function in your calculator and then copied it in. Make sure that you put the important, label the axes, and also write the function there. You should really put these points because you lose points if you don't actually put where it crosses the axes. So here we know that point is 3 and we know that point is 1.5 there. Example 12 again, so it's the same example but question B. By using antiderivatives, find an expression for this definite integral in terms of x. Well, we take that function in there and we say, this is a derivative of something. What is the something? Okay, here the steps over here. To find the antiderivative of that, basically you want to find out what is the function that would give that as a derivative. A function whose derivative is 3 minus 2t. The derivative of 3t is 3, right? So it must have a 3t in it because the derivative of 3t is 3, and there's our 3. The derivative of t squared is 2t, and we have a 2t. So it looks like the function that this would be a derivative of is 3t minus t squared. Because the derivative of 3t minus t squared, from what we know about derivatives, remember, there's a 1 there, so the 1 comes down the front, and that becomes 3. The t becomes 1 minus 1 to the 0, so that just becomes 3 when you take the derivative of that. When you take the derivative of this, the 2 comes down to the front, so it becomes minus 2t, and then what you take 1 away from the 2, that's a 1. So that would be 3 minus 2t. So we found that function that would have that as a derivative. Now, remember, this definite integral is actually this minus this, as we saw that in earlier in this video. So we substitute x into this one here, we substitute x into that, and we've got 3x minus x squared. So t equals x into that, we've got 3x minus x squared. Then we substitute 0 into this, and we get 0. So the final answer is 3x minus x squared. And then exercise 13F. Rather than go through and give you hints, I just suggest that you go back, have a look at those examples, and also have a look at the first page of this video, or the first part of this video, and you'll see similarities, especially with the notation. You'll be able to look at it, and from the notation, you should be able to figure it out. This exercise will give you practice for understanding what the notation actually represents. Go back to the beginning of the video if you're unsure. Example 11b should help you with these. Example 12 should help you with 9, 10, 11, and 12. They already have the integral here, so that's a good start, very similar to example 12. Here you'll have to actually first write the integral, and you know how to write an integral from a graph because we practiced that in previous videos. So write the integral and then go through the steps of example 12.